Okay. Yeah, come on in. Sign in. So I've said to some of you already, this is not going to be a really interactive session. Since MATLAB is a licensed product, we don't want to use all licenses up, so instead you'll just sort of, I'll lecture and then I'll show you some examples, but you won't be really working with those examples yourself today. So let's get started. I'll go ahead and start off by introducing myself a little bit, and that's going to go ahead and introduce the purpose and the background on this class as well. So, I'm Dave Godlove. I work at the High Performance Computing Center here. My area of expertise is neuroscience, and I did neuroscience work for about 6 years to get my graduate degree, and then I came here and I was a postdoc for 2 years. And during that period of time, I used MATLAB quite a bit. When I came here, I wanted to analyze some data using Biowulf, but I didn't really know anything about a Linux environment, didn't know any programming languages outside of MATLAB. And so I approached Biowulf from a very MATLAB-centric kind of place. I actually replaced bash scripting essentially with MATLAB scripting. And so that's the kind of the way in which I'm going to be teaching this class. It's focused on how do you use Biowulf. It really, you just want to use MATLAB and you want to do it from within MATLAB. How do you use Biowulf from that perspective? I want to let you know right from the get-go, though, a lot of the things I'm going to show you today, there are better ways to do a lot of the things that I'm going to show you. If you want to take some time to learn bash scripting, if you want to take a little time to learn Python, a lot of the things that I'm going to show you, you can actually do a lot more easily in those languages. But if you want to get up and running fast and you want to learn about Biowulf, this is a good kind of like gateway to start doing that. Okay. Yeah. Cut off a little bit. So the class is going to be broken up into 2 parts. In the first part, I'm just going to lecture, essentially. I'm just going to, tell you about the things that you need to know in order to be able to run your MATLAB code in parallel in Biowulf. And in the second part, then we're going to take a break, and then the second part, I'll actually go through an example. So I'm going to start off by talking about, what are the steps to setting up your code and running it in parallel in Biowulf. Those steps are going to be, first, to start developing your code interactively on the Biowulf system. Then we're going to talk about the need for compiling your code and how to do that. When you run your code in parallel, there's several different ways to do it. I'm going to be suggesting that you use the swarm program, and so I'm going to show you how to write swarm files, or rather, how to have MATLAB write swarm files for you, and then how to execute those swarm files. I'm going to talk about monitoring jobs, and once again, monitoring jobs from within the MATLAB environment. And then we're going to take a break, and then we'll get into part 2, which is going to be a concrete example. For that, I'm going to be showing you how to process a lot of image files in parallel, and that is going to be, that example is what you've just copied into your data or your home directory. So after this class, you can open that up, and you should be able to just fire it up and run it, step through it, and see how it's working, and it should be working code. But before I get started into the outline, I just want to review very quickly a few MATLAB commands. Many of you might be very familiar with these. Some of you might be unfamiliar. Some of you might not have used them in a little while. So I just want to review them and make sure that everybody's kind of up to speed on them. Okay, so hopefully you've run in at some point in time to this fprintf command. It gets its name from the C programming language. So let's say I take a few variables here and I set them so that they're strings. So name equals Mary, adjective equals little, noun equals lamb. So I got 3 strings now. If I use fprintf with these escape sequences, then everywhere where there's escape sequence, it's going to use kind of like a fill-in-the-blank sort of routine to plug those escape sequences back in, and that's going to print out to the screen, Mary had a little lamb in this example. Okay, so a related function is sprintf. Okay, so sprintf is similar. We're going to do exactly the same thing, except now I'm going to call sprintf, and I'm going to set that equal to a variable. So sentence, in this case, equals sprintf, these escape sequences. And now sentence is going to equal this entire string, Mary had a little lamb. So I can use sprintf to build up, strings. Maybe I could have commands in there, with arguments and so on and so forth. Another command that I use quite a bit that a lot of people don't like, but I'm going to hopefully try to make a case for it, is eval. So eval takes a string and says, whatever this string is, I'm going to pretend that's a MATLAB command, and I will evaluate it just as though it's a MATLAB command. So in this case, I'm setting two variables equal to these two chars. So notice that part 1 is 6 and part 2 is 7. These are actually not numbers, these are chars. Then I'm going to concatenate together this string, ultimate answer equals space, part 1, space times part 2. And then I'm going to evaluate that string, which has been concatenated together here. And when I evaluate that, the ultimate answer equals 42. It equals 6 times 7. Okay, does everybody kind of see that? This is really ugly because I'm concatenating all this stuff together with spaces and so on. It's a little bit hard to read. So the eval command is often used in combination with sprintf to make things a little bit easier to read. This is the same example, but now I'm saying eval sprintf, ultimate answer equals two escape sequences multiplied together, the 6 and the 7. And so then the ultimate answer, when I evaluate that entire string, which is built using sprintf, it's going to end up being ultimate answer equals 42. If only we knew what the question was. And a related function that maybe fewer of you have seen is eval-c, so eval with capture. I don't really know if that's what it stands for, but it makes it easier to remember. So now I'm going to do exactly the same thing. I'm going to eval sprintf, ultimate answer with these escape sequences, but I'm actually now going to eval-c, and I'm going to set a variable, my string, equal to whatever the output is going to be. Okay, so that doesn't print anything to the screen, but then if I type my string equals whatever was going to be printed out to the screen with new line characters and white space and all that kind of stuff. So you might be wondering at this point in time, okay, who cares? Why are you showing me all this? So hold on to that for just a second. I'm going to show you one more command. Okay, this is actually more just a, not so much command as it is just a symbol. So this symbol, the bang, you can also use system, the function system. They do the same thing. In this case, say I'm in MATLAB and I type who am I at the command prompt. MATLAB doesn't know what who am I is. It's going to give me an error. Well, let's say I'm on the Biowulf system or some Linux system. I type bang, who am I? Well, now it's going to tell me. It's going to tell me my username. You can use that in combination with that eval-c that I just gave you. And I could set user equal to eval-c, bang, who am I? Host equal to eval-c, bang, host name. And what that's going to give me is some information about who I am and where I am. I could then take that information and then use it to do things in the Linux environment. So this little set of commands right here allows you actually to do quite a lot in the environment. So the bang will allow you to issue system commands. Eval-c will allow you to capture the output of those system commands. You could then parse them, and you can use sprintf to plug those things back in and make more commands out of them, and then you could execute those in MATLAB or at the system. This is a lot of what bash scripting is. So this now allows you in the MATLAB environment to do a lot of what you would be doing in bash or in Python or Perl or some other scripting language normally. Okay, so that's just a little intro. Now we can start going along with the outline a little bit.
Do you think there's any advantage to using the bang over man?
I don't know. I don't think so. I prefer it just stylistically, but okay. So now let's start talking about developing your code interactively. All right. So the first thing that you're going to want to do when you're developing your code interactively is you're going to want to start an interactive session. And for the examples that I'm going to show you today and the kind of the philosophy that I'm going to show you today is that you're going to be running an interactive MATLAB graphical user interface on Biowulf. You're going to be, developing your code in that interactive session, and then you'll be submitting jobs through that interactive session and monitoring them and so on. So you need to know how to get onto Biowulf, right? And in order to do that, you kind of have to understand a little bit about the cluster. So every 4 months or so, we offer a class that's all about high-performance computing at NIH. It's a really great class, and if you're going to continue doing this, you should take it. I'm not going to go into detail, but I'm just going to give you a little bit of a flavor of what the cluster is like. So when you first log into Biowulf, and I'll talk to you more about how to do that, you land on a particular computer called the login node. It runs on a machine that looks like this. It's actually a virtual machine, but the login node is kind of like your gateway to the rest of the cluster. And there are a lot of different users on the login node. They are, doing a lot of different things. But critically, you can talk to the batch scheduling system, which is Slurm, once you're on the login node. So that allows you access to the system. If you're, how many NIMH users do we have here? Okay, if you're an NIMH user, you've got the added benefit of you can use Felix. And Felix is Slurm aware, whereas Helix is not Slurm aware. So that's helpful because then you can do all the things that I'm going to be showing you here just from Slurm. Or just from Felix, rather, sorry. Okay, so you're on the Biowulf login node. The thing is, you can't fire MATLAB up on the Biowulf login node. Because there's so many users there, and because this node is so critical, you're not allowed to do anything computationally intense. So you have to ask the login node for resources, okay? And those resources are going to be CPUs and memory. And in our case, we're actually going to be asking Slurm for licenses as well. Those are resources that we're going to be wanting to use. Okay, those resources are not going to be on the Biowulf login node because you're not allowed to use the Biowulf login node. They're going to be out on a Biowulf compute node somewhere. So once you issue the appropriate command, your session is just going to be warped to this new place, and you're going to have the resources that you've asked for. That compute node is going to sit in a rack somewhere. It's going to be in a Biowulf partition. You might be familiar with, there are several different, so if you just submit your job normally, it'll go to the norm partition. There's also the B1 partition, which is made up of compute nodes, which we've reclaimed from the old iteration of Biowulf. And there's a quick partition for jobs that move quickly. There's a large memory partition. And some of you might have access to other partitions that your center has bought into. So if you're an NIMH person, you've got your own partition that you can use. If you're a CCR person, you've got your own partition, so on and so forth. So that partition sits somewhere in the cluster. And then we've got storage, which is mounted to all the nodes everywhere throughout the cluster. So on that, anywhere that you end up being, you can see your data, you can see your same directories, you can see your code, all that follows you around wherever you go. Yeah, Brian.
You mentioned a bunch of different clusters that I didn't know about, like quick node, like a quick job or a large memory. How do you know whether or not you should be sending something to those as opposed to one of the normal nodes?
If you type the command freen, F-R-E-E-N, and hit enter, you'll get a list of all the different partitions. Okay. And they'll give you things like the number, they'll give you stats about the nodes that are in those partitions. So you'll get the number of CPUs, the amount of memory, so on and so forth. The quick queue, so really you should go to the HPC website and read more about it. I don't know everything off the top of my head. The quick queue is for jobs that are going to finish rapidly. I don't know what the definition of rapidly is, but I would imagine it's 30 minutes, a couple hours, something like that. Large memories, obviously, for those types of jobs. There's only 4 nodes. They have a terabyte each of RAM, so they're essentially like a Felix for your own, job. Let's see, what else is there? There's the B1 part. So you would use B1 if there's a lot of volume on the norm partition, and you don't really need some fancy computational resources. You can get by with whatever's in that, partition. And it's not currently available, but when we upgrade to the newer version of Slurm, which I think is going to happen fairly rapidly, we're already running it in the development mode. You can actually submit to multiple partitions with a comma-separated list. And so let's say I want to utilize both the norm and the B1 partition. I can give it both those arguments, and then my job will split up and run on whatever's available at any given time. Okay, so how do you actually do all that? What are the commands necessary to do all that? Well, the first thing you would do is you would issue some sort of an SSH command, or you would use an SSH client or something in order to actually get to that Biowulf login node. You're then going to enter this sinteractive command with some arguments, and I'm going to go through these in a little bit more detail. You're then going to load the module from MATLAB, and then after that, you'll actually fire MATLAB up. This is how you can start an interactive session on Biowulf.
Are these slides going to be available?
Yeah, definitely. I'm going to put all these up on the website. The last class, slides are very similar. They're already up on the website. Yeah, so you don't have to memorize all this stuff. So when you use SSH, you're going to want to use this -y argument. That's going to set up your X Windows environment to allow you to see the graphical user interface. And you might not actually type this at a command prompt. It kind of depends on what operating system you're using and what client you're using. You might be using something like PuTTY, X132. I think those are more like GUIs. You just click on something after you set it up, and it gives you a terminal. Xquartz, you would actually use this. And if you haven't started using NoMachine, you should all, I'm going to show you NoMachine a little bit later on. You should all at least look into this. When you're programming, like at home, when you want to log into an interactive session and start messing around and programming something up, NoMachine's a lot faster. So if you ever experienced that you got that like lag in MATLAB when you're trying to program, or you're going to experience it if you haven't, over a slow connection, NoMachine's actually very helpful. And this is a website you can go to learn, how to install any of these on your system, and what the steps are for firing it up and using it. Okay, so then you've got your SSH session started up. Then you have to type a command to ask for resources. So Slurm, which stands for Simple Linux Utility for Resource Management, is the batch processing system that runs the cluster. Because it starts with an S, most of its commands start with an S. So sinteractive is the command that you would use to allocate an interactive session. And in this case, these arguments that we're giving it, -C4, we're saying we need 4 CPUs, and mem equals 4G. I'm saying I only need 4 gigabytes of memory, whereas normally with 4 CPUs, it would allocate 8. And then I'm giving it this -L argument and a bunch of MATLAB licenses. When you run the example that I'm going to give you later on today, this is the list of licenses that you're going to need to make this run appropriately. And once again, these slides will be online. I'll go ahead and send an email out to all the people in this class with the location of the slides so you can download them easily.
In this README file inside the directory, you have this copy. It is different syntax for the sinteractive. It's -- license MATLAB. Is that an older version? Or?
Those are equivalent. A lot of Linux commands have both a short version and a long version. And so that would be the long version, and this is the short version. Not on the cluster, but you can certainly use it for development on your own desktop before you, go up to the cluster. So yeah, and maybe this is a good time to talk about licenses too. So licenses are kind of a mess on the cluster, MATLAB licenses. So most of the time people come from academia and they had a site license. And, you know, they don't have to worry about compiling their code, doing any of this stuff, because they have as many licenses on their cluster as they want. They all just work. We would love to buy a site license. That would be great. The MathWorks will not sell us a site license. They only offer those to people who are in academia. And they say that NIH is not academia, we're government. So they say that if they opened it up to government and started allowing site licenses to us, they'd have to do it for everybody. So in any case, I've been talking with the rep. I'm in active discussions with the rep, trying to get our license situation into some sort of a better model, but right now it doesn't look like there's an easy solution. I should let you know that we are moving in the direction of not allowing non-interactive MATLAB jobs to run uncompiled. So we're moving in the direction where if you want to run an interactive session, you want a MATLAB license for that, that's fine. And you can do that anywhere. You can do that in the cluster. But if you try to spawn off, you know, some non-interactive batch job and it starts asking for a MATLAB license, we're going to disallow you to have that license. Because what's ending up happening is that people are checking out licenses incorrectly, or they're checking them out correctly, but other people are checking them out correctly. Their jobs are failing. So we're having all kinds of issues because of that. So just so you know, this might be an important skill for you to learn in the future. Oh, so I already went through S Interactive, allocating what you need, and then here's the licenses. Okay, so now you're on an interactive session.
Licenses. Does the website have a list of the shorthand for those? Because, like, you know, it's image processing toolbox, but you're only writing image. So does it tell us, does the website have that list? So if I know I need the image processing, I can go there and find out what the actual name is?
You know, I don't think the website currently does, but I'm going to fix that. Right now, this is like a little known fact, but the way that you can get that shorthand, there's a licenses command. Let me just bring up a terminal here, and then we'll have a look at it, if I can. All right, yeah, there's a licenses command. I can't look at both at the same time. So let me... Okay, so licenses gives you the total number of licenses that we have for each product, and it gives you the number that are available for use combined on Helix, Felix, and Cyware. And then it also gives you what Slurm thinks the current state of the licenses are. And this is often grossly inaccurate. And this is the reason that we're having so much trouble with the licensing system, is that there's no way to get Slurm to talk with the license server. It's just not something that the developers of Slurm care about. So if you want some more detailed information about this, might be hard to see. If you type licenses and then give it the -V switch there, that's verbose mode. And what that'll do is it'll give you the number of licenses that are currently in use on Helix, Felix, Cyware, and Biowulf. So that we have 3 Cyware users right now using the main MATLAB license, 1 Biowulf user, and 2 Felix users. Your question, if you want, I'm sorry that's being cut off. If you want to know what shorthand you should use, licenses -H. The help will give you all the short names of these things. You can actually use these as input to licenses to query licenses about specific licenses, the numbers of licenses that are currently available. Okay, so, but back to the, firing up MATLAB and running it. So now you're on an interactive node, and you've got all the resources you need. So now you have to actually load the MATLAB module, and that's going to set your environment up to be able to use MATLAB. So you just module load MATLAB, and then if you're using any other programs like AFNI or something, you would type module load AFNI. You can use different versions if you want. The default's always going to be the latest version that's installed. And then you might use just MATLAB. If you've set up your environment with X Windows and you type MATLAB or MATLAB and, you're going to end up getting the familiar graphical user interface. But you might not, you might be working at home on a slow connection or something. You might not want to use the graphical user interface, in which case you can type MATLAB no JVM, or if you don't have an X Windows environment already up and running, you're going to get this anyway, just the non-graphical interactive session. Okay? All right, so then you'll type away and you'll develop your code and it'll be great and you'll be able to analyze all your data. And then, once you're finished doing that, you'll want to compile your code. Okay, so why do you want to compile your code? Well, compiling your code removes the need for MATLAB licenses. So this is the reason that we're thinking about forcing people to compile their code if they want to run it non-interactive, because once you compile it, you don't need the MATLAB license or any of the toolboxes anymore. So that's a tremendous benefit. So that, in turn, allows you to run hundreds or even thousands of instances of your code in parallel, which can greatly speed things up. So how do you do it? Well, it's pretty simple. You would type a command similar to the following. So mcc2-m myfunction-m. The -m tells it that you're going to be compiling your code to be called in the terminal, essentially. You're not compiling your code to be like a C library or a Python library or anything like that. It's going to be essentially standalone code. And I'm not going to cover how to do those things today, but you can check it out. It's on the website.
Can I do this on my Mac MATLAB license and run it on the HPC? Is it cross-platform like that?
So two things. Number one, you might not have a compiler license.
Yeah.
Yeah, and those are, when you get all the little parts that you need to put it together and actually make it work, they end up running about $20,000. But if you have a compiler license, and you compile it for Mac, you might be compatible, but you probably ought to compile it for this environment. If you compile it for Windows, it's not going to be compatible. Mac, might be, I don't know. So you can do this at the command prompt at the terminal, or you can also do it just within MATLAB. Okay, it's a function, and because it's a function, you can also use a more functional version of the syntax like so. This is helpful if you want to use this in common. If so, maybe you don't know the name of the function that you're going to compile. When you write the code, you want your code to figure out what the name of the function is that it's going to be, so you can use those sprintf types of tricks that I was showing you earlier to just plug things in. Once you execute this command, it's going to produce several new files in the same directory. So you might want to cd to a new directory, or you might want to, there's an argument that you can give MCC, which will tell it to make these files in a different directory. If we assume that the code is called myfunction.m, then it'll produce one called myfunction, which is just a binary. It'll produce another file called run_myfunction, run_myfunction.sh, so it prepends run_appends.sh. And then there's going to be a few other files that, for our purposes, are not going to be that important today. Today, we're just going to focus on these two files.
Sorry.
Yeah, sure. Sure.
Is it possible to tell the MCC function what is your target processor that you're going for, Windows?
Yeah, actually.
So going back to this question, from his Mac, you could compile for Linux and then be happy.
Yeah, so you actually can give it arguments to say, don't use just the default compiler that you are going to use something else. I haven't messed around with that too much, so I don't know how well it works. Okay. So now you've got, this thing's compiled. How do you actually call it? How do you execute it? Well, you're going to call that shell script that was generated, the one that's called run_myfunction.sh. And then you're going to give it some input arguments. The first argument is going to be the location of the MCR, the MATLAB component runtime, which is the product that MATLAB puts out that makes this code run without MATLAB. Then after that, you're going to give it just whatever your normal variables would be, whatever your normal input arguments would be for your function. Okay? And I'll talk about all that in greater detail as we progress. But before you compile your code and decide you're going to execute it and do everything like that, there are some things going back to developing your code that you need to be thinking about as you're writing code in preparation to compile it. So let me step through some of that stuff. One thing that a lot of people like to do with big long analyses is that they'll be printing things to the screen. So they'll say, okay, loading file X, processing file, dot, 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 dot. When you actually compile your code and you end up executing that using Swarm, you're going to end up with an output file that's going to have all that stuff in it. And if it's not diagnostic, if it's diagnostic, then that's fine because it can tell you where bugs occurred. But if it's not diagnostic, it's just going to be noise that you're going to have to sort through in order to try to figure out, if you did have a bug. So you might want to suppress that. Figures also, if the figures are not the point of the analysis, if they're just kind of trying to show you, would you mind signing in? Thanks. If the figures are not really the point of the analysis, then you might want to suppress them when you're running things in parallel. Okay. Yeah, and so these are the reasons that you might not want to have your code doing that. There's an easy way. You might want to write a function that you can call in an interactive session, but then you can also compile that function and have it run non-interactively, and either way will be just fine. And there's an easy way to do that. There's a built-in MATLAB function called isDeployed, and it's going to return just a 1 or a 0, just a true or false. And so if I've got a figure that I don't want to print to the screen when I've got my code compiled, I can just wrap that figure in this little statement, if not isDeployed, pop up a figure, plot x against y, and pause. Once I compile my code, that's no longer going to be executed. That's just going to go ahead and progress anyway. Okay, another thing to think about is that every function that you call has to be on MATLAB's path. Okay, and I want to stress that that's at compile time. So a lot of times, what people do is that they'll have a main function, and then it'll say add path, and then all these new paths where all the other functions are. And so when it runs, it sets up the path for MATLAB. Well, when you compile your code, you're not running your code. So if it compiles, it's not going to know that that add path is there. It's not going to see any of the other functions that are supposed to be on the path, and it's probably going to look like it compiled, and then it's not going to work when you try to run it. So you have to make sure that everything's on your path at compile time. Another thing, I really think you should avoid using CDs in your code too. The reason for that is because you're implicitly changing your path. Wherever your current directory is, that current directory is always on your path. So if you're bouncing around, you could be CDing to a directory which is not, explicitly on your path at compile time, and then your compiled code might end up not working in a mysterious way. Okay, and so I'm going to pause for a second. I'm going to ask you, is that all? How are we doing? Is that all kind of clear? Any questions so far?
Path I didn't actually understand. Some of it looked like you were enabling a path in interactive code.
Yeah.
I didn't figure out what you were saying not to do.
Yeah, so you wouldn't do either of these. So MATLAB has got a way. So MATLAB and Linux have sort of opposite philosophies about paths. And a lot of times when people come from Linux to MATLAB, they don't really understand it, and vice versa. So so Linux says, by default, you're not going to have hardly anything on your path. And if I write a function and then I CD somewhere else and then I type the name of that function, I'm not going to be able to see it because wherever I saved it probably is not on my path. And that's good because it prevents name conflicts and all kinds of bad things that could happen. MATLAB by default says everything in the world is going to be on your path, and your path is going to be 1 million characters long, and if you call any toolbox that we've written that you've got installed, it's going to automatically be there. And we expect when you write your code that you're going to add everything to your path, and then you're going to save a variable which is going to be loaded the next time you fire MATLAB up, which is going to make sure that your code is on the path too. And that's got drawbacks as well, but if you're going to compile your code, you kind of have to work within MATLAB's philosophy and do that, and make sure that all your functions are on the path saved and ready to go when you compile your code.
So, just to clarify on that, if you had everything, when you compile the code, if the code would have run in MATLAB then, because you had everything on the path, once it's compile, it's good to go. You don't need to re-add paths before running the compiled code.
It's not necessarily true because, like I said, you can change your path on the fly in code. So it could be the case that your code runs just fine, it doesn't run into any issues where it doesn't know where a function is, but then you try to compile it and it doesn't run properly. You could get lucky, you could run it once, and everything gets added to your path, and then after that you compile it and it's okay, but then the next time you fire MATLAB up, you try to compile it before you run it, then it's not okay. It's better off just to have everything on your path and know it's there explicitly.
Side point, is Biowulf working? No.
I don't know. Let me.
Helix was okay, but Biowulf.
Well, this session is on Biowulf. Yeah, so let me exit and then try to log back in. Yeah, it's working for me. Biowulf is behind the. Can you log in from Helix to Biowulf? You might be on the AirNet. So, yeah, the AirNet is not within the AirNet's in the DMZ, so it's not within the real trusted network. So, when you guys go home and you want to log on to Biowulf, you have to log in through Helix or use a VPN. Biowulf is not open to outside. Helix is, so that's a quick way to get in. For now. Okay, now the reason I paused there and asked for questions is because this is a little bit more complicated. So the things I've been talking about up to now are a little easier. This kind of a lot of times confuses people at first. And so that is, once you compile your code, it's only going to accept strings as input. And don't worry about that. It might make you panic at first, but there are ways around that. And I'm going to show you some ways around that. So what do I mean by that, first off? Okay, well, let's say you've got input 1, input 2, and then all the way up to input n. Let's give it a concrete example. Let's say my first input is going to be a 3. My second is going to be a vector of 1, 2, and 5. My third one is going to be a cell array. So this isn't even going to work because there's white space in there. But let's just pretend for a second that did work and it didn't throw some weird error. Once you actually get into MATLAB, this is what MATLAB is going to think that you just did. It's going to say you called my function with a char, 3, and with a couple of strings, one of them having some white space and some square brackets, and another one having some commas. That's actually not that big of a deal, though, if your code is prepared that if it sees one of these strings, it needs to convert that back into whatever you intended it to be. Okay, so your code has to be ready that if it's expecting a double and it gets a char, then it's going to say, no, input 1 is supposed to be a double, so input 1 equals char to double input 1. Does that make sense? Okay. This looks a little uglier, but it's a lot more flexible. And I'm going to be showing you instances in which the first will not work, in which the second will work. So what we're doing here, forget about the eval for a second, just think about the sprintf. So sprintf, input 1, equals the contents of input 1, right? So once we construct this string, it's going to say input 1 equals 3. And then if we evaluate that like a command, it's going to say input 1 equals 3. And then our input 1 is magically going to be a double called 3. Okay, is that clear? Because I'm going to be talking about that a lot. No? Okay. So, is the first part clear? Why your compiled code only accepts strings as input?
In input 1, you use, for example, when you put the exact value or you put the variable.
So that is going to be a char. So input 1 is it's not a variable. It's going to come in as a char. So let's say this is input 1. Right there.
Okay, and in your code, do you use 3 as the replace the input 1, or you always use this name as input 1 or 3? read?
So yeah, in this code, that input 1 would be a special name. That would be the name of a particular variable. And that's how this would work, is it would be looking for the name of a particular variable, which is the position that variable comes in as. And then it's going to say, okay, well, given this name or given this position, which in MATLAB, in the functions I'm going to show you are the same thing, it's going to convert that back into what it literally is.
What is the maximum number of entries?
Oh, I have no idea. More than you will need. Yeah, I would imagine. Yes, more than you will need, because I'm going to show you, if you're thinking about passing vectors or arrays or things that are really, really large, I'm going to show you a better way to do that.
And so every step, the result is a string,
Right.
right? And eval, what does
Eval, we went through this at the beginning. Eval takes as a string as an input, and then it says, this is a MATLAB command. Evaluate it as though it's a MATLAB command. So let me just, so once again, let me just go through the whole thing. So Bash is not a typed, I don't know if you call Bash a language or not, but Bash is not a typed language, if it's a language. What that means is it doesn't have different data types. It says, I'm going to look at whatever you give me, and I'm going to use the context in order to sort of figure out how I should treat these things. So if you give it the number 3 without any context, it defaults to strings and chars. It's just going to say, that's my default. In this case, when we call this function in Bash, it's got 0 context. All it knows is it's passing some stuff to another function and whatever, it'll let that thing deal with it. So it's going to pass it as strings or as chars, always.
So that's one issue. Just
Yeah.
converting everything from strings to...
Yeah, right,
Okay.
right. So then your function gets that as a string, always. And if you're expecting a double or an int or any other data type, you've got to be prepared to convert it back to that data type. So this example, if I was just to write, I'm not going to call this thing input 1, I'm going to call it x. So if x equals 3, note the single quotations making this a string, right? And if I say eval sprint f x equals an escape sequence, comma, x. So let's forget about the eval for a second. What's that going to give us? That's going to give us, here, let me do a little syntax highlighting to make this. That's a string. This is a string. And then this part is a string too. Right, so this string is going to take the contents of this and plug it into this escape sequence, which is sprintf. So if we just looked at whatever this variable ended up being, it would be x equals 3 with a semicolon at the end, right? And then if we wrap that in an eval statement, it's going to evaluate that string as though it's a command, and now our x, which started off as a char, is going to end up being a double. Okay. And this is like the most complicated thing I'm going to go over today. So if you get this, it's downhill from here. Okay. Yeah, and once again, so you might want your code to work at the command prompt or within the MATLAB environment, and also worked in compiled mode. So you might set up a little test to say, if is_char input 1, do this little magic, convert it to a double, but otherwise don't do anything. I've probably already given it a double. Okay. Okay. So you've covered all the bases. You've thought of everything you could possibly think of. You're ready to compile your code. How do you do it? Well, in MATLAB, the compiler license, the compiler toolbox, ships with a function called MCC. So the way that works is you type MCC -m myfunction.m, but don't use MCC, okay? This is something which is specific to NIH. When you use MCC, just like when you use any other licensed product, it's going to check out a license to your interactive session, and then it's going to hold on to that. I already said the MATLAB compiler is really expensive. It's like $20K. We have two of them. We have two of them for the entire campus. So if you're doing some interactive code and you use MCC, for as long as your interactive session is open, you're going to have that license, and then people are going to be upset because they're going to want to compile their code. Instead, here at NIH, we've written this wrapper function called MCC2, and so it should work identical to MCC. It's all the same everything, except what it does under the hood for you is that it opens a new interactive session of MATLAB. It passes everything, all the arguments that you gave it to MCC, and then executes that MCC, and then it closes the interactive session of MATLAB, and so your license is only out for as long as you're compiling your code, and then you give it back when you're done. So if we all use MCC2, we can all use the compiler license, and everything's cool. Right now, you still have access to MCC if you really want it. The reason is because MCC2 has not been widely used yet. It might have bugs in it. So if you find that you can compile your code with MCC, but you can't compile your code with identical arguments to MCC2, email me. That's a bug, and I need to fix that.
How do you get to that .m file?
Yes. I'm going to tell you. So MCC2, just like MCC, sits in the MATLAB compiler toolbox. But if your cache is out of date, you might not be able to see MCC2. So if you can't see it, just type rehash toolbox, and it'll find it for you, and then you'll be able to see MCC2. Was that your question?
Was that .m file? Is the original file? Or I saw you have original .sh file. That is original? Would you find the...
Yeah, so the .m file is your source file. That's your MATLAB function that you are writing. And then when you compile it, that's when you get your run_x.m, or .sh rather.
Originally we get the .m file, and the compile we get as
You don't get it so much as you make it. I mean, you might get it from somebody else, but this is the code that you're writing. You can use it either in the terminal, or you can use it within MATLAB itself. Yeah, so it's a function in MATLAB, but it also does double duty as a... Actually, the function in MATLAB, I think, calls actually the compiler outside of MATLAB. So you can call it outside of MATLAB, or you can call it from within MATLAB.
And it has to be owned by who? It's not like on Helix, for example.
No, you can compile code on Helix. The compiler license works on Helix. Yeah, it should. It's in the same place as MCC, so yeah, it should work just as well.
Stepping back to the beginning, what is the relationship of Biowulf to Helix?
Oh, that's a good question. Yeah, okay. So Helix is just one giant server, and it doesn't run Slurm. It's just a Linux server. And it's got, I don't even know, 64 CPUs, something like that, and like a terabyte of RAM. And it's like the Wild West. Everybody logs onto Helix and just runs whatever they want to run and beats it up and, use it to do analysis or to troubleshoot your analysis, just whatever you want. There's a similar big server for NIMH users called Felix, but those are just what they are. They're just one server. Biowulf is, it's like, I think right now it's like 32,000 processors, and it's going to be up to, we're buying another 30,000, so it's going to be up over like 50 or 60,000 processors pretty soon.
So there's never a reason to do something on Helix, right? That's the case.
Some people don't have Biowulf counts.
Oh, I see.
Yeah.
So if you have Biowulf, then it makes sense to get in via Helix to Biowulf and then just do everything in Biowulf, even if it's something that's simple like this.
Yeah, in practice, I very, very rarely, if ever, use Helix. So, yeah. Okay, yeah, you would type rehash toolbox if you can't see your MCC2. Okay, so you're compiling your code. Great. You need now also to think about how is your code going to run after it's compiled. So there's some options, there's some arguments that you can give the compiler to change the way that your code runs. Okay. When you fire MATLAB up, you might be aware there's some runtime flags that you can use, like no JVM, for instance, which means no Java virtual machine. I kind of showed you that really briefly earlier. You can use similar arguments to your compiled code, and the way that that looks is you use the -R switch to let it know that you're giving it a runtime argument, and then the name of that argument, and then another -R and another name of an argument. I want to talk about this single computational thread argument for a second. That's important. So MATLAB wants to be helpful. And so you fire it up on your desktop or whatever, and it looks around and says, okay, you got 4 processors here. So when you start running certain functions that my engineers have optimized for me, I'm going to fire up 4 threads to run on all 4 of these processors. And I'm just going to do that under the hood without you even knowing, and your code's going to run faster, and it's going to be great. Problem is, when you get onto the normal computational node, it's going to look around and see 32 CPUs, 16 hyperthreaded processors, and it's going to be like, oh, great, okay, I got a lot of resources here. But usually, you've only allocated 2. The default allocation is 1 hyperthreaded CPU. So MATLAB doesn't know it's running under Slurm. Slurm doesn't know about MATLAB. The two don't talk to each other. And so it's going to fire up 16 or 32 threads when certain functions are run that are all going to run on your 1 CPU. And that's going to possibly hang the node, definitely slow your code down, and it's going to attract the unwanted attention of staff members who are going to start emailing you and saying, you know, what are you doing? You're not using resources properly. So to prevent that from happening, there are instances in which you might know that's going to happen, you might want it to happen, but unless you're very sure of what you were doing, you should use this single computational thread runtime argument, and that's going to tell MATLAB, you know, don't do all that. Just run on a single thread, and then everything's going to be fine. Okay? No display is something, so sometimes you've got figures that you're, yeah, and sometimes figures can really mess things up. If you work hard enough, you can usually get compiled code to make and save figures for you, although it's a little bit difficult. If you're running under the correct environment, you might, and you've got 1,000 jobs running, and they're all doing, 5 figures, you might start getting like 5,000 figures all trying to be printed on your screen at once, and that's going to, crash your system and possibly mess your job up. And so that's a safe thing to do. That's a good question.
But you can avoid the no display if you're not going to have 5 million.
Yeah.
It will work.
Yeah. Yeah, I usually throw it in there just for safety's sake.
The other question is if there are certain computational processes that are not easily split up into separate processes, then, but yet under the hood, MATLAB does a better job of running them as multi-threaded things. Actually, not running this is a good deal, right?
It could be. You could allocate yourself but when you submit your job, it could be, but you'd have to be aware of that, and you'd have to set it up so that when you submit your job, you take the whole node.
Okay.
Because
you can ask for that.
Yeah, you can do that. There are ways to do that. All right. Just one more word about figures too. If you're running in a non-X Windows environment and you're printing figures, if you set it up right, they won't print, and you won't get any errors, but you will still get those figure objects and that you've got access to through the handles and everything. And so because of that, you can actually save your figures as PDFs or as .figs or whatever, and have them afterwards, even though you didn't display them. Sometimes that's a pain to get set up, though. Okay, I haven't talked a whole lot about the MCR, the MATLAB component runtime. So let's talk about that a little bit. So on our system, the MATLAB component runtime, which is always going to be the first argument when you use this shell script, which is generated by MCC, it's located in this particular location. User local, MATLAB-compiler, and then there's a million of them. And you have to know what version of MATLAB you compiled your code with, and you have to match that up to the correct MATLAB component runtime. This is kind of a little thing that trips people up a lot, and it doesn't give you a very understandable error when you mix and match. So unfortunately, they're not backward compatible. You've got to know which one's which, and you've got to use the correct one. And you don't have to memorize the location of that or which ones go with which. You can just log on to our website instead. Mouse is there it is. And we've got essentially this table which will let you know which component runtime matches which MATLAB. Okay, and this is even more esoteric. Just ignore that for a second. So when you actually run your code, once again, under the hood, what MATLAB does is it's going to make a hidden cache directory for you. And it's going to put all the components of your code that it needs to run into this hidden cache directory. It's hidden because it's got a dot in front of it. By default, that's going to go in your home directory. That's where it thinks is the best place for it. Your home directory is on a network file server. If you spin up 1,000 processes that are all running in parallel, and they're all running a lot of different functions, then all 1,000 times however many functions are in there are all going to start hitting that one directory, and that can really slow your code down. So to avoid that, because it's a network directory, so to avoid that, and just to show you, if I go to my home directory and I type ls-al and then I grep for MCR, these are all the hidden MATLAB caches that I've got in my home directory because each one corresponds to a different version of MATLAB, so I've run a lot of compiled MATLAB. You can tell MATLAB, though, that you want it to put that cache directory somewhere else. And the way that you do that is by setting an environmental variable. Excuse me. So if you're not familiar with Linux, Linux does a lot with environmental variables. They're usually all caps with some underscores. And MATLAB running under Linux knows to look for this environmental variable called MCR cache root. And so if you set that equal to, let's say, temp, your username, and then MCR cache, that's where these cache files are going to be located. So on a compute node, temp is local. Temp is not a file share anymore. And so that makes it run faster. In fact, temp is RAM. So this is going to make it run really fast because now you're actually taking all your code and just loading it onto RAM and leaving it there, and anything that needs to access it is going to be able to access it very rapidly. I've shown you how to do that. So you could set this environmental variable at your terminal before you start running your code. You can actually set it within MATLAB. So here's a way to do that. So we're going to say user equals dblank. Dblank removes leading and trailing and white space from strings. So user equals dblank eval c, who am I? That's going to end up being godlovedc if I run it, or whatever your username is. And we'll use set environment, or set env, and then we're going to set this equal to this. So this is the MATLAB equivalent of exporting an environmental variable. So you could have that in some MATLAB code, which spawns some swarms, or you could just do that manually, or that run.sh file that I showed you, you could manually stick that in there after you make that. You couldn't have that in your MATLAB code that gets compiled, though, because once it is compiled and starts running, it's already going to be running with your local cache. It's not going to be able to change where its cache is at. Okay, so that's compiling code.
Just so I understand properly, if you're compiling code that you want to run many, many times, you wouldn't want to put it in the temp directory then, right? Am I misunderstanding what you're putting there?
So yeah, so the way that that's going to work is that it's going to make that temp directory, and that temp directory is going to be gone when your job's done running because it's RAM. So either, if you're going to run it like in multiple sessions, either you would always have to have a mechanism to set up that environmental variable, which that's why it would be a good idea to put it into a submission script, or you know, it's just going to, when you don't have the environmental variable set, it'll still run, but it'll just put that cache into your home directory like it normally would.
Okay. So it does. You don't have to. This isn't something particular about the compiler. This is about running the job.
Yeah, this happens. I'm pretty sure. I haven't checked this to be 100% sure, but I'm pretty sure this doesn't happen when you compile the code. Well, I'm pretty sure because I just messed around with this last night. It doesn't happen when you compile the code. It happens when you actually call your compiled code.
Okay. What's in the cache?
The cache contains all kinds of stuff. It contains binary versions of your code. It contains pointers to your code. This is one of the reasons why funny paths don't work, because it actually sets up a different directory, and if you've got paths that are being checked after compile time, it'll start looking at those paths, and those paths don't look anything like, you know. So it's got a lot of stuff. You can check it out. It's you know, it's hidden, but you can get into it and look around in it.
Make sure so you wouldn't necessarily recompile code every time you run it. Or somewhere and then.
Yeah. And compiling takes time and it takes licenses, so you probably, unless you change something, you know, you don't want to compile it every time. Okay, so now you've got compiled code. It runs. It's great. You want to start running in parallel. So how do you do that? So I'm going to explain. There's multiple ways to do that. I'm going to explain to you how to use a program called Swarm, which is also an in-house program. You won't find that at other places. This was written largely by David Hoover, who's a staff member here at HPC. All right, so Swarm calls the slurm function sbatch. So sbatch, I told you that slurm functions tend to start with S. Sbatch is the way that slurm allows you to submit a batch job. And so you could use sbatch directly if you want to, but Swarm, it's a little bit easier. So the way a Swarm works is you give it a file, and on every line of the file is a single job. And Swarm just parses that and says, this is all the jobs that I'm supposed to run. This makes things a lot easier because then Swarm sets up the sbatch command and then executes it for you. Swarm's got a lot of options. It's got man pages, so if you type man swarm, it'll tell you all the options. In fact, there's even a mechanism for passing it sbatch arguments. So if there's options that you just can't get any other way except for using sbatch, you can still access them via Swarm by passing it sbatch arguments. And finally, if you want to start using sbatch instead of Swarm, there are ways to capture the actual command, the sbatch command that was built for you, and then you can kind of bootstrap from that and start to understand how to use sbatch. So it's a good way to start. Using Swarm is a two-step process. The first thing you have to do is write a file. That's a Swarm file, and that file is going to contain a single command on each line. More precisely, you're going to write code that's going to write the file for you, most probably. And then second, you actually have to call Swarm, and you have to give it as an input argument that file that you wrote or that you had written for you. Okay, so to do a concrete example, let's say, once again, I've got that function, run my function, or my function that I've compiled, and I've gotten back this Swarm script, run my function.sh. Let's say I make a Swarm file. I'm going to call it myjobs.swarm, and it's going to start 4 processes. So this is what that Swarm file is going to look like. And I'm going to run it with 4 different parameters. Okay, so you'll notice that over here on the end, the way in which each one of these jobs runs differently is that each one's got a different parameter. Okay? So is that clear? Okay. So what you're going to do after you save this is you would call Swarm and, give it this file.
How do you get the .sh file?
The .sh file you get by compiling your code.
From the .m file?
Yes. You start off with myfunction.m, run mcc2-m myfunction, and then it ends up giving you run_myfunction.sh. Okay, so this is only 4 lines of code. You could write this really easily in an editor if you wanted to, but what if it was 400 or 4,000 lines of code? Oh, wait a minute. I'm sorry. This is the command that you would use then to submit this file that you've got saved to Swarm and have it run in parallel. Okay. So let's say you've got a lot of lines, though. You don't want to write it yourself. You want to have it written for you. So how do you write code that writes the code? So here's a quick little example in MATLAB for how you can generate a Swarm file, actually generate that Swarm file that I just showed you. So this is actual running code. You can copy it out of the PowerPoint when you get it later and mess around with it. So let me show you real quick what it does. So first I'm going to be setting a cell array equal to 4 strings, param1, 2, 3, and n. So then I'm going to initialize an empty variable, command list equals null. And so now for ii equals 1 to the length of param list, I'm going to take and set command list equal to whatever's already in command list plus run myfunction.sh space plus user local MATLAB compiler space plus param list ii and then a new line. And so this is going to end up building all 4 of those commands in this case. Then I will open a file called myswarms or myjobs.swarm. I'm going to open that with the W+ option, which is actually going to overwrite any file which already exists. Save the file handle. Then I'll use the file handle with the fprintf command to write command list into that file, and then I'll close the file. So then if I execute this, I'm going to end up with exactly, these contents in a file called myjobs.swarm. Okay, see everybody nodding their head?
I'm confused. MATLAB code to generate the Swarm, MyJobs.swarm?
Yeah. And so here, this is trivial. It's only 4 lines. MyJobs.swarm is only 4 lines of code. This is,
Okay.
but if it's 400, 4,000, you can just add to this parameter list, and then this code, this Swarm file is just going to end up growing and growing and growing. Okay, so now I'm going to revisit the most fun part that I talked about earlier. Remember that inputs are only strings, so we're going to talk about that some more. Okay, so we've already handled the case in which these would be, 1, 2, 3, and 4. That's very easy. We just turn those back into doubles. What happens if you decide you want to supply arrays as input arguments? How would you represent the array as a string? I think this is maybe what you were asking earlier. Okay, well, if you really want to do this, and by the way, you probably don't want to do this. An easier way to do it would probably be to generate all your variables and save them in files, and then to give your functions a file location as an input and allow your function to load the contents of that file. And then it would know that whatever the contents of the file, that's where the variables are. I'll show you how to do that in a minute. But let's say you really want to do this. Okay, well, there happens to be a function in MATLAB called mat2string, matrix to string. You can give param1 as input to matrix to string. I'll show you what that's going to give you here in a second. And then I'm also going to put a set of double quotations on the outside of this so that it plays well with bash, okay? So once I concatenate all that together, it's going to end up looking like this. So note that minus the double quotes, this is the command that you would supply to MATLAB in order to generate, this array. Okay? So you could put something like this into your code, into your code that generates your swarm files. You might end up with something that looks like this. So Bash is going to be very happy with that. It's going to think that that's a string, and it's going to, call your function just the way it ought to. But then you're going to have a problem when you get back into MATLAB. You wanted an array, a two-dimensional array. You got a string that looks like this. It's going to have this double quotation stripped off of it by Bash. Once again, this is that instance in which the string to double command won't work, or string to double command won't work, but the eval sprnf command will work just as well on this as it will on anything else. It'll convert that string back to that array. Okay? Now, to get really, really fancy, just to beat a dead horse a little bit, we could also do other data types. We could do cell arrays if you want to get really fancy. There's no equivalent cell to string as there is mat to string, but you can write the code yourself, and it's not really that complicated. So in this case, I'll be saying param string equals nothing, and then it's going to be similar to what I showed you before, where I'm going to be building up not a command, but actually the parameter string here. So for I equals 1 to the length of param1 up here, param string equals whatever's already in param string, plus a single quote. This is MATLAB's escape sequence for a single quote, param1 II, another single quote, and then a comma. Okay? So I'm going to end up having something in param string. It's essentially going to be all these with single quotes and commas interspersed between them, and then one comma at the end. Then I can take that param string and I can say everything except for the last comma, so 1 to n minus 1. Go ahead and concatenate that with some curly braces and double quotes. I end up with something that looks like this. It's the command. Hopefully everybody can see that. Sorry, it's down at the bottom. It's the command for making the cell array plus double quotations on the outside. Then your swarm file might end up, looking something like this. Then you've got a similar problem. Once again, you get back into MATLAB after calling your swarm file, and you have to be able to interpret this string as a cell array. Once again, that trick that I showed you before is going to work for that. So eval sprnf param1 equals, the contents of param1. That's going to give you back the cell array. All right, if you're doing that, then you're kind of, so this is the kind of stuff that I was talking about that you can do in MATLAB, but it's easier to do in a scripting language like Bash or Python or something like that. Furthermore, if you're doing that, it might be better to just save your variables in files and then just load the files. So what that would look like, let's go back to the previous example of arrays, okay, because I can generate random arrays easily in MATLAB, just for an example. So let's say I want to pass this array. Okay, so I can write some code. Excuse me. Oh, I'm sorry. I need to point this out. I can generate that array that I showed you before and similar arrays with this command. Rand4 is going to give me a 4x4 random array. I'm going to multiply that by 10 and then round it so I get random numbers between 1 and 10. I'm actually going to be calling that down here. And so what now I'm doing is I'm saying I want 4 files. I can set this number to whatever I want. I'm going to name a directory. Mat directory equals home, mat directory. I'm going to say if that directory doesn't exist, if not is dir mat directory, make directory mat directory. So if it doesn't exist, make it. For I equals 1 to file n, in this case for I equals 1 to 4, my param is going to be a randomly generated 4x4 matrix of numbers between 1 and 10. I'm going to come up with a file name to save that in, and that's just going to be sprnf escape sequence.mat, and that escape sequence is going to contain num to string II, so this is essentially going to be 1.mat, 2.mat, 3.mat. And then save, full file takes a directory and a file name and puts them together with the correct slash in there. So I'm going to save full file, mat directory up here, file name, and then I'm going to stick the parameter in there. What this is going to do is it's going to make a directory for me. It's going to fill the directory with 1.mat, 2.mat, 3.mat, and each one of those is going to contain an array, a 4x4 array of random numbers between 1 and 10. So now I've got the files. How do I run them? Okay, well I could have some more code that says, give me the name of the matrix directory, the mat directory, file list equals what mat directory. Many of you might not have seen this what. What's like dir, dir. It gives you the contents of a directory, but it's a little nicer in that it gives you a data structure back, and that data structure has some fields in it which are specific to MATLAB. One of the fields is .mat. So if you use this, you'll get not all the files, including dot and dot dot, that are in the directory, but you'll actually get just the mat files in the directory. It's a little bit nicer. And then the rest of this code is going to look almost identical to what I've already showed you for how to build a swarm file using a bunch of parameters, but in this case, those parameters are going to be file names. So this is identical to what I showed you earlier, except for this line right here. For simplicity, I just said file list II. Note that I could say full file matdir, file list II here, and that way I could have absolute paths to each one of these in my swarm file. Okay. And then finally, I'm just going to open a swarm file, write the contents to it, and then close it. And after executing all this, I'm going to end up with a swarm file that looks like this. Or it could have absolute paths if I had modified the code. And then I can just execute that on all of those mat files in the directory. And note that for this to work, my function has to be written so that it takes a file name as input. At the beginning of the file, it loads the file name, and it looks for, in this case, param in there. And then it will have, param equals to the 4x4 matrix, and then it'll have some code that runs param. Some people are nodding, and some people are not. So we have some time. Yes.
It's like something where you can say, well, someone could write code, all of it.
Yes. This is the purpose of this class. So the example that I'm going to show you, so you shouldn't be doing any of this with the command prompt. You should write code that does all this for you.
I mean, what I'm thinking is, most of us are very, very similar things. Why doesn't anything like that exist that does it for you?
So I've thought about writing, I've thought about that a little bit. One thing I could do is I could write a function and hand it out to users that takes the contents of a directory, and then you give it the location of a directory, a script, and an output directory. And then it'll set up a swarm for you that'll run that script on the contents of the directory and give you output files in another directory. I've thought about that a little bit. The reason I haven't done it yet is because it's pretty easy to do it yourself. And so some people on staff wonder why I'm teaching this class, right? Because if you're a Biowulf user, shouldn't you learn bash scripting? If you don't learn bash scripting, you might not be a savvy enough user to use the cluster the way you want to, right? So there becomes this trade-off of like, well, how easy do we make it? Can we just make a GUI where you can just press a button and fire up a swarm? And if we do that, are you really analyzing your data the way you think you are? Or what happens if your jobs run away? Are you monitoring them? And, but I might in the future. I don't know. Okay. I think that's all for writing swarm files. The only thing that's left, you've written the swarm file, that's the hard work. Then you just have to call the swarm file, right? So you can do that in the terminal by saying swarm-f myjobs.swarm, but we don't like the terminal. We're doing everything in MATLAB, right? So you can also do that from within MATLAB, obviously. The same command, you just put a bang in front of it. We can get even better than that. We can capture the output of this swarm-f command, and we can take that and stick it into a variable called job ID. If we do that, we're going to save. So every time you run a job, it's going to get this specific identifier under Slurm. This is how you reference that job and monitor it and do things to it. We can save that so we don't have to manually copy and paste that. Now it's in our code. And so what can you do with that? Well, I'm going to show you that you can monitor jobs. That's one thing that you can do with it a little bit later on. But another thing that you can do with it is you can set up dependencies. And this is really great. So I'm going to go back to the terminal. Let's pretend that we're not in MATLAB for a second. You fire up a swarm, and it gives you this output, this job ID, and then you would say swarm-f another job. So you've written another swarm script called another job.swarm, and you would give it this argument: dependency equals after any. In other words, I don't care if you fail or you're successful, and this is the job ID to be dependent on. What that'll do is your second job will wait until the first job is finished executing before it starts running. Okay? But that's boring. Let's do that in MATLAB. So once again, we do job ID equals eval c. We'd capture the output of job ID, and then we can use eval with this sprintf command to go ahead and give it a formatted print statement with this escape sequence. The escape sequence is going to be filled with job ID, and then our second job ID pops up here. Now we got two jobs. One's going to run after the next. And in fact, with this syntax, and you can just type the same thing again and again and again, or have in your code the same thing, and you can line up one job after the next after the next. So you might have, for instance, so why is this useful? You might have, for instance, let's say you have data, you don't know what the size of the data is going to be coming in, but you know you want your code to break the data up into manageable chunks and save it all in some directory. And then you want to, run through that directory and analyze all the data that's in that directory. And then you want to take all those chunks and you want to put them back together into reconstruct them into a full, data file again. So you can run three jobs that do that: deconstruct the file, analyze all the chunks, and put it all back together again. And if you set the dependencies up right, then you can just set it and forget it.
What about random number generator? Run multiple jobs. How would be random number generator?
Oh man, that. Well, it's going to be local. Let me think about that.
Could you repeat the question?
Yeah. Sorry. Random number generator in MATLAB always does exactly the same way. So what would be the best way for when you use RAM in the code to make sure that it doesn't always do exactly the same thing?
That should be a feed number.
Yeah.
Yeah, that's a great question. I hadn't thought about that.
Use the time, fixed time.
Yeah, but then if they have exactly the same time point.
Yeah, that's really excellent question. So I don't know. I'd have to do a little research on that because MATLAB saves the state of the random number generator, and then it starts with whatever. So it might be that if your jobs start even briefly asynchronously, then that gets saved because these jobs are still associated with you and your environment, your MATLAB environment. So that would be an interesting thing to test. I could test that quite easily. Yeah, and if they do start at identical times, you couldn't see them with the current time unless you get down into microseconds.
Just with the job number, assume not even delay, you could just add in that. If this is job X, you
Yeah.
add X to your random generator C.
So each job number is going to have, so Swarm is going to give you a job array where all the job numbers are going to be identical, but the sub-job numbers will all be different. It'll be 1, 2, 3, and so on and so forth. So yeah, you could add to the time. You wouldn't want to just seed it with that, because then if you ran two subsequent jobs, then you'd come out with the same result, but you could add it to the current time. shoot, I started writing a list of things to do. Amend the website to give a list of licenses. And make sure, send me an email or something later, and I'm going to send some emails out to some people that I know that do computational modeling on clusters, because they run into this same problem, and asking what they do about it. Okay, I think this is all on Swarm. Okay, good. And so monitoring jobs, the last thing, monitoring jobs is pretty easy, pretty straightforward. So there's a whole slew of different commands that you can use to monitor your jobs. I'm just giving you a few of them here. SQ is good for before your jobs start, so it'll give you information about your jobs, even if they're sitting in the queue pending, not started yet. Job load and sjobs give partially overlapping, but not completely overlapping, information about jobs that are currently running. And job hist, job ID, will give you the history of a job after it's already finished running. Most of these take both the job ID or the username to just show all pending or running jobs. Once again, it's trivial, but if you want to do this in MATLAB, I'm going to show you some code that does this automatically, and this will be the syntax. So you do eval sprintf, bang sq, and then the job ID would be the escape sequence here, or you could just use the user environmental variable, which I introduced on the very first slide when I told you to copy the code to your own directory. So that's really pretty straight. Based on everything I've told you so far, this should be pretty straightforward. Okay, and then when your jobs start executing, there's going to be two different text files which are going to be saved either wherever you executed the job from, or in a different directory if you tell Swarm to save those in a different directory. Those are going to be your .o and your .e files. Your .o is going to contain standard output, and your .e is going to contain standard error. If you're not a Linux person, you might not know what those things mean off the top of your head, but in MATLAB, this is the stuff that you print out to the command prompt, and this is the stuff that MATLAB prints in red to the command prompt. Okay. All right.
Is there a way to suppress both the O and E files?
I don't think there's a way to suppress them. Wait a minute. You might be able to. You might be able to just send them to dev null. I don't know. You'd have to check man Swarm. That would be a option in Swarm.
Back to the path you mentioned a while ago. So would you recommend just having absolute paths for every script you call, or is it just that you want to make sure the path is right when you compile?
When you compile your code, every single function that your code calls and every subfunction that your subfunctions call, you should be able to type which and then the name of the function at the command prompt and be returned a path. If you type which and the name of the function, you don't get a path back, then your code's probably not going to compile properly.
You were mentioning not to use add path and not to use cd during within the code.
Yes. So instead of CDing, I think that you should use absolute paths. Yeah. You might get away with it. It might work okay, but it's an error that I've seen people have before.
And the add path would generate an error, or would it just generate one?
It won't generate anything usually except for code that doesn't run.
Okay. But if you added the path during compilation.
Before compilation. And that's probably the hardest thing about compiling code, is to make sure that everything is where it's supposed to be and that all the paths are correct. Okay, so you guys want to use the bathroom, get a drink?
Just a comment. You're absolutely right about the scripting versus learn bash. That's totally wrong.
Yeah.
This is the path,
Yeah.
You spend 15 years in the monastery. what you're
Right.
supposed to know.
Right.